All right, in this chapter, we started off in section 4.1 talking about inverses, one-to-one, domains and ranges of those things. And so it all led up to us being able to find an inverse. Bless you. We know an inverse is like the opposite of a function. What happens if you compose something with its inverse? You get out x. They cancel each other out, and you get x back. So if I ask you to find the inverse, remember the very first thing we did is change f of x to y. Would help if I could write. Okay, you don't have to write these steps out, but for our review purposes, I'm going to. So that would be y equals 4 over x minus 3. Then what an inverse does is it flips x and y. So that's what we do next. Switch x and y. So then it becomes x equals 4 over y minus 3. Then what do we do? We have to solve for y. So I would multiply to get rid of my fraction. So if I multiply over my y minus 3, I get xy minus 3x equals 4. We're trying to get y by itself, so we can add over the 3x, divide by x, so y is 4 plus 3x over x. Step 4 was change y to f inverse of x, just to show that we found the inverse. So our inverse is 4 plus 3x over x. That's the opposite of the original. They would cancel each other out. With those, we always talked about domain and range. The domain of the function, that's the x's in the original, those turn into the y's of the inverse. So the domain of the function and the range of the inverse are the same. Domain is pretty easy to find in a fraction. What do we know? In a fraction, we can't have 0 on the denominator, so x can't be 3. So the domain of my function, the range of the inverse, is everything except 3. Negative infinity to 3, union 3 to infinity. It's harder to look at something and know the range, but the range of the function is the same as the domain of the inverse. So if I look at my inverse, I know the bottom can't be 0, so x can't be 0. So that would be negative infinity, 0, union 0 to infinity. All right. So everybody should be able to find an inverse, and you should be able to identify domains and ranges from that. Now make sure, I talked about this at the time, you can't just say D equals R. I need to know the domain of what is equal to the range of what. So you have to tell me the domain of the function is equal to the range of the inverse, and then give me that interval. All right, so that was really what section 1 was about. We did some more within it. You know, we had, before we actually found the inverse, we were able to tell if functions were inverses or not. Even if I asked you one of those, could you just find the inverse of one of them and see if you got the other one? Absolutely. So it all boils down to being able to find the inverse. Are there any questions? Section 2 was all about exponentials, and section 3 was all about logs. So let's talk about those. We should be able to solve equations. So let's start off with a couple exponential equations. I tried to put some challenging ones up here to get our brains going. What was our strategy on these? Common base. Okay, so I have 64 and the cube root of 4. What could I change them both to? 4. Okay, so 64 is 4 to the third. Okay, a cube root of 4. How would I write that? Okay, notice I put those in parentheses because when you have a power to a power, what do you have to do with those exponents? Yeah, multiply them out. So that's 4 to the 3x. Over here we distribute, so we get 4 to the 1/3 x plus 1. Once you have the same base on each side, you can drop the base and set the exponents equal. So if I subtract over my 1/3, I get 8/3 x equals 1. So then divide by 8/3 or multiply by the reciprocal, and x is 3/8. Nice thing about these, you can always check them just by plugging it back into your calculator. On B, so we need the same thing. We have to get a common base. What can I change 9 and 27 to? Okay, so 9 would be 3 to the, and 27 is 3 to the, again, power to a power, we have to multiply those exponents. So we get 3 to the 6x minus 2 equals 3 to the 12 minus 3x. Once you get to that point, you can set your exponents equal. So if I add over my 3x, I get 9x. If I add over my 2, I get 14. So x is 14 over 9.
How do you check it?
You go back to the original and you just plug in both sides. So like, I would type in 9 to the minus 1. And then I do the other side. You're welcome. Other question?
So this is section 14.
Mm-hmm. So there'll probably be 2 or 3 of these types of equations on the test. Are we okay with it? Or quiz, not test. Less scary, quiz. All right, in 4.3 we were solving similar equations but with logs. So let's say I gave you a couple log equations. What was our strategy on these? We always start by putting them in exponential. To put it into exponential, you start with the base. The base of the log is the base of your exponential. And then you just go across the equal sign. So 4 to the 3rd power equals 7x plus 4. That is the hardest step. If you remember that definition, this is actually a pretty easy problem to solve. So 4 to the 3rd, 64, equals 7x plus 4. Subtract over my 4, divide by 7, and x is 60 over 7. Remember, on these, the argument has to be positive. If I plug that in, it is. And you can kind of reason through it if you needed to check it. You know, you can talk yourself through it. It would be log base 4. If I plug that into 64, remember, a log is giving you an exponent. 4 to the 3rd power does equal 64. So I I know I've done it correctly. All right, on D, if I'm changing that into a log, where do I start? Or sorry, into an exponential, where do I start? Your base would be x to the fifth equals 32 over 243. Okay, if I'm solving for x, how do I get rid of a fifth power? Do I need a plus or minus? Nope, because it's odd. Okay, fifth root of 32 is 2. The fifth root of 243 is 3. So we just get 2/3.
How do you do the fifth row on these?
Yeah.
Oh, yeah, I keep forgetting.
Oh, if you do 5, so push the 5, and then second, the caret, that'll put it.
Oh, sorry, yeah.
Get it?
Yes.
Yes.
So 5. Oh. All right. Do we need any more log or exponential equation problems? Okay. Next thing we talked about with our logs, expanding and condensing. That's what we are doing Friday. So if I asked you to expand the first one, what would you write?
Log to the
Log base 4 of a to the third. Where do we put exponents?
in the front.
Good. Okay, it was multiplied, so we add log base 4 of b. Divided by, so we log base 4 of c to the fourth power. Where do you take the fourth power?
In the front.
So things multiplied, you add the individual logs. Things are divided, you subtract the logs. Exponents turn into coefficients. All right. If I ask you to condense, that means I'm trying to write this as a single log. What do I do with this 2? So that's x squared. Minus, so I would be by my y. Minus, so was this going to go on the top or the bottom? The bottom. And the 3 would turn into an exponent. So x plus 1 cubed. Which one? Okay.
I'm doing it with her, like, okay, this is not bad. I see.
It's always just like word.
Shall we do this together? We should just do this one question.
Can we like do the odds? Like is that
All right. The other thing that we talked about in 4.2 and 4.3 was graphing exponentials and logs.
Oh.
Okay, I have a couple log problems. I have some log problems up here, but I can add more, or we could do an exponential if we needed to. On the logs, if I asked you to graph them, what did we always do? We made a t-chart, and how did we do that? If I started with this, what? Yes, I'm going to put in -1, 0, and 1 for the exponent. So first, let's write this in exponential form. So if we start with our base, that's 2 to the y power equals x. You have to know how to go back and forth between the log and the exponential. When you have a log, write it as an exponential. So, since y is the exponent, we always graphed exponentials by putting in -1, 0, and 1 for the exponent. In this case, y is the exponent, so it goes in for those. What is 2 to the -1 power? What's 2 to the 0? And 2 to the first? So if I plot those. 1/2, -1, 1, 0, and 2, 1. Remember, logs always have an asymptote, a vertical asymptote. What kind of asymptote do exponentials have? Horizontal. So graphing an exponential is the same, except in those, the x is the exponent. So that's the one we'll plug in -1, 0, and 1 for. It's always, for a log, it's the y-axis, because you'll never be able to do 2 to a power and get 0.
So it will always be on the y-axis.
Unless I move it left.
If it's a log.
Okay, then we would use that as a parent function to get any other. So if I ask for log base 2 of -x, okay, if my x is negative, what does that do to the graph? Over. If it's a negative on the x, that would be like coming in and making the x's negative, so it flips it over the y. So my points, you can either get it from here or from my t-chart, but just make my x's negative, so we get -1/2, -1, -1, 0, -2, 1. So that just was a reflection. So we used our transformation rules still with these. Remember, logs have a vertical asymptote, exponentials have a horizontal asymptote. So if I ask you to condense, start with your coefficients. Any coefficients just turn into exponents. Okay, so I can write my 4 and my 2 as exponents. I am writing a single log if I condense. So we have the x plus 4 to the 4th. Minus, so where does the next one go? On the bottom. X minus 1 squared. Plus, so where does this one go? On the top. Plus log base 3 of x, we just multiply it with x.